Hi, linear algebra students. So this is the first video of the makeup classes of invertible matrix theorem series. I'm aiming for 4 videos of less than 10 minutes each. Hopefully I will succeed. So first, very important for this series, I will ask you to either print the page 1 of the lecture notes where the invertible matrix theorem is, or keep your book open as you follow these examples with the invertible matrix theorem written right there. Okay? Because the first thing that we will do is we will use it to determine if these 4 matrices are invertible or not. It's the most straightforward application of the invertible matrix theorem. So let's get going. Our first matrix is a 2 by 2. So one thing that we could do to determine if it's invertible or not is just to compute the formula for the inverse of a 2 by 2, right? 1 over AB minus BC and so on. So, however, it's worth noting that if you look at the columns, okay, so this matrix is the matrix A1, A2, okay? Its columns are linearly independent because they're not scalar multiples. And I'm not expecting you to prove that they are not scalar multiples, like you get this by inspection, but I do expect you to state that. Okay, so in other words, a complete answer would be that A1, A2 is linearly independent since they are not scalar multiples. And as a result, it means that A is invertible. And this is the result. E implies A. Okay, E being that the columns of A are linearly independent. Okay, the B, to answer B, what you have to notice is that the 2 rows here are multiples. So notice these rows are multiples, are scalar multiples. So we will take advantage of this to prove that the matrix is actually not invertible. So one thing that we could do is, and actually, yeah, let's do it. We will take B transpose to be, and yeah, let's actually keep the blue. I would like to have a full color board, but let's actually keep the blue. I think it's clearer if I use each color for the color code. So B transpose. Now you're gonna write each of these rows as being columns. Okay, so 2, 4, -4. Okay, and without introducing too much notation, let's just say that the columns of B transpose are linearly dependent of B transpose are linearly are LD. And now again you have to tell me the reason. Since the third column is twice the first. Okay, so you could also put labels, but since it's B transpose and not B, you have to kind of be careful. But let's just say this. The columns of B transpose are linearly dependent. So what does it mean? It means that B transpose is not invertible. Okay? And this is from, again, E implies A. But since B transpose is the transpose of B, it means that B is also not invertible. So B is not invertible. And this is from the last statement of the invertible matrix theorem. So it is L implies A. Okay, by the way, I forgot to box the answer on this guy. So let's do it. And box the answer here. All right, if we look at C, okay, C, there's not that much obvious stuff to do because the columns are not scalar multiples of each other's and the rows are not. So there's nothing obvious that jumps to the eye. So your best bet is actually to row reduce it. So you would do here, like, okay, I will have row 3 becomes row 3 minus 2 row 1. And the resulting matrix would be this. So 1, 2, 3, 0, 4, 5. And then you have 0, 0, and then you have 2. And as you can see, the idea is that you have 3 pivots. So there you go. They're right here. So C is 3 by 3 and has 3 pivots. Meaning that C is invertible. And this is statement C of the invertible matrix theorem, is C implies A. Okay, so boxing this. Now D is pretty much the exact opposite, right? So right here, okay, you can see that the third column of D, the third column of D is not a pivot column. I just want to emphasize, this is a general remark, that to make arguments on the pivots of a matrix, you do need a row echelon form. But D is already in row echelon form, so you're fine there, okay? So for that reason, D is 3 by 3, but has only 2 pivots. So as a result, D is not invertible. From, again, C implies A. All right. Hopefully this was helpful. So in the next video, we're gonna see, we're just gonna cover a warning. So remember that the invertible matrix theorem works for square matrices only, and that's what we will see. So see you there. Hopefully this video was helpful.